All right, silly people, here's the situation. Um, we have a mass that is attached to two springs, um, which have equilibrium position B or equilibrium length B, um, and it's allowed to move in the x direction only. So it's moving back and forth while attached to these two springs. And we have to solve for this problem uh, to a second order approximation using perturbation theory. Um, so, perturbation theory in this context, we're looking for the change in angle over time as second order in A, I think it says, um, which means we're going to be looking for um, some angle beta, which is going to be dependent upon some average of beta dot times t plus some constant beta naught. We're looking for the beta dot term. Uh, so that's going to come about using action angle variables and stuff. Because I think beta dot is going to be equal to um, del delta H del J averaged, something like that. So let's just start off the Hamiltonian stuff. Um, the potential for this is going to be 2 times a Hooke's law spring potential. So we're going to have just K up front. And then we have to have the length of the spring at a given time, which from the geometry of the problem is going to be a squared plus x squared minus the equilibrium length b squared. And the kinetic energy term is very simply mx dot squared over 2. So the Lagrangian is mx dot squared over 2 minus k square root a squared plus x squared minus b. All right. What we want to do with this is we actually want to simplify the potential term to bring a outside of the radicand. A 1 plus x squared over a squared. And then look at that, we have something that is primed for using a binomial expansion. What I mean by binomial expansion, it's a Taylor expansion around the stuff that's here, which is supposed to be small. That's going to look like 1 plus x squared over a squared will be equal to it's going to be 1 and then 1 over 2 x squared over a squared squared minus 1/8 x squared. Actually, no, that term isn't squared. This term is. Yeah, plus some higher order terms of order x to the 6th. Okay. Let's put that into our Lagrangian. X dot squared over 2 minus k. We have a plus x squared over a squared. No, it's just over a. Minus 1 over 8. It's supposed to be 2 over 2a. We're just going to write it as x fourth over 8a cubed all minus b in that squared term. Cool. From here, let's just go ahead and get that Hamiltonian going. So P is del L del x dot, which is just mx dot. Um, so the Hamiltonian will read px dot minus L, which is going to be p squared over m minus p squared over 2m plus that polynomial that we just found. This is an approximation. Pretty close approximation though. Okay. P squared over 2m plus the approximated potential term. Okay. Let's expand the squared term now. I think that's a fair thing to do. We'll have k a squared plus x fourth over 4 a squared minus or plus some x eighth term that doesn't matter. I'm leaving out anything that has a order higher than 4. All right, so an x eighth term that doesn't matter, a b squared term, a minus x squared over 2, or actually just minus x squared. So minus x squared and a minus x fourth over 4a squared minus 2ab plus bx squared. Actually, it's minus bx squared over 2a my plus bx fourth. It's just going to be over a, and that's going to be over 4a cubed. Polynomials, we love expanding them. So we have some terms that cancel out, which is lovely. That term cancels out that one. And then essentially what we have is some kind of constants. So I'm going to actually factor the k through and collect constants. So we'll have k a squared plus b squared minus 2ab. That's all going to be a constant. Plus, I'm going to put this as k over 2 in here. Minus 2x squared. That shouldn't be minus, that should be plus. Plus 2x squared minus 2bx squared over a. The reason I'm doing that will become apparent. And then finally we have kbx fourth over 4a cubed. Now, I'm going to call this a constant c. And I'm going to factor out the kx squared term there. So it's going to be kx squared over 2 times 2 minus 2b over a. That's another constant. plus kbx fourth over 4a cubed c p squared over 2m is h. Now I'm going to call this constant gamma. And so what we'll have when the dust settles is something that looks a lot like, I'm actually going to put the k inside of there so that all of that is a constant. K there, k there. We're going to have gamma x squared over 2 plus kbx fourth over 4a cubed. Now it's really obvious which of these terms is the perturbation term. It's this one. That's delta H, the perturbed Hamiltonian, where this stuff is H naught, the unperturbed Hamiltonian. The problem that we're looking at really only depends on delta H, so that's pretty nice. What we're going to do next is pretty much just plug in the solution for action angle variables for the harmonic oscillator into this delta H. So that's kb x fourth over 4a cubed. The other reason why I put all of that k nonsense into a constant gamma is so that I can then resolve that constant for gamma and put the perturbed Hamiltonian in terms of gamma. I'm going to go ahead and do that. What is that going to be? Gamma equals 2k minus 2bk over a, so k is equal to gamma over 2 minus 2b over a. Cool. Rewriting the perturbed Hamiltonian then, it's going to be bx fourth over 4a cubed 2 minus 2b over a. Yeah. Now we can use the solution of the position for the simple harmonic oscillator, which is used a lot in Goldstein. It's x equals m pi omega naught eigenfrequency times sine 2 pi w, where w is just an angle. We'll just plug that into the perturbed Hamiltonian and simplify things a bit. We'll have b up top. We'll have 8a cubed. Let's factor in a through. 8a squared a minus 2b times j squared over m squared pi squared omega naught squared sine fourth 2 pi w. Awesome. Let's then take the partial derivative of delta h with j. This is going to give us our beta dot, which is going to be it's going to be bj over 4a squared m squared pi squared omega naught squared a minus 2b. sine fourth 2 pi w. Okay. Um, Now we're going to take an average of this. Um, in perturbation theory, the only thing that really is going to change over time is the 2 pi fourth, or sine to the fourth 2 pi w. Everything else is pretty much treated as a constant in time. So we're just taking the average of this, and that's a known average. It's 3 over 8. Um, so the average is just going to be that stuff times 3 over 8, which gives 3bj 32a squared m squared pi squared omega naught squared a minus 2b is how the angle changes in time. So that's in I think in the problem it says that it's a correction to the frequency. Um, Correction to the frequency. So what happens when A approaches B is something that the problem considers then. Uh, what happens when A approaches B? Um, this term. So I made an algebra mistake somewhere. Actually, that should be none of those factors of 2 should be there. And this is to illustrate the fact that when A approaches B, the denominator gets smaller and smaller, and so the correction to the frequency starts to become a lot larger than the usual frequency, um, omega, which means that the motion is probably going to stop oscillating and start being really weird. Either it's shooting off into space or just staying completely still.